from the Precision Neurotherapeutics lab at the Mayo Clinic, and he'll be talking to us about a data-driven approach to characterizing glioblastoma subpopulation dynamics.
Hi everyone, thank you to the organizers of this mini symposium for inviting me to speak. As Kevin mentioned, I'm talking again about glioblastoma, which a lot of the talks today have touched upon. I am based at the Mayo Clinic in Arizona under the supervision of Dr. Curtin. I'm a postdoc in her lab. So a bit of background about glioblastoma. It might already cover what some people have touched on already, but it's the most common and aggressive primary brain tumor. Unfortunately, there hasn't really been a shift in the standard of care for some time now, and the average survival is still 15 months from diagnosis to the patients passing away. Unfortunately, this disease remains uniformly fatal, and due to the location of the tumor being in the brain, you can't really often go and take samples of the tumor itself. So there's a clinical reliance on MRI. There's two types of MRI that are traditionally used, and there's T1 weighted with some contrast they inject into the body and shows up on MRI in regions of vasculature that's broken down due to the presence of the tumor. That's usually considered the region where the tumor bulk is, and that type of imaging also shows necrosis where there's some cell death, which tends to be central to the tumor. Then the other type of MRI is T2 weighted, which typically shows edema, which is water that's leaked out of vessels that are kind of in the process of breaking down. And that's traditionally thought of as where the infiltrating tumor region lies. Unfortunately, MRI doesn't show the whole picture. As I mentioned, it's hard to go in and get biopsies of this tumor often because you don't want to keep having surgeries, quite an invasive surgery on patients. But there is a lot of genetics going on under the surface in this disease. Two particular genetically distinct subpopulations of interest are those that are upregulated in endothelial growth factor receptors, which I'll refer to as EGFR throughout this talk, and platelet-derived growth factor receptors, which I'll refer to as PDGFR. So here on this figure, you can see one patient that had two biopsies taken, one of which was shown to be amplified in EGFR only, and not PDGFR, and one that was shown to be amplified in both. And tracking this patient over time, you can see that these two regions recurred at different times, suggesting that they have different underlying dynamics going on, which could be related to these amplifications. Unfortunately, the spatial dynamics of these different subpopulations isn't really well understood. It could be a reason that clinical trials which focus on EGFR upregulated subpopulations haven't shown great results so far. So we're looking to use GBM biopsy data alongside some mechanistic modeling, ideally machine learning, which I'll speak about towards the end of the talk, to understand how these subpopulations interplay with each other. Do they compete against each other? Do they cooperate with each other and promote each other's growth? Or do they kind of just mutually interact, maybe only competing for space or nutrients? So here's an outline of this talk in general. I'll start off by talking about the ongoing clinical trial we have, which is looking to take image localized biopsies from different regions of the tumor to try and understand where these subpopulations lie in individual patients. I'll then talk about how we analyze these biopsies for their genetic makeup, and then introduce a mechanistic model, which will be similar to those introduced by some of the previous speakers today. We have a reaction diffusion equation. I'll talk about some results of this model, and then talk about how we might use this for some model selection to try and understand how these subpopulations interact. So first, image localized biopsies. We try and take at least 6 biopsies per patient, ideally 3 from the T1 GAD enhancing region, which, as I mentioned before, is that central enhancement, which is shown in dark blue on this video on the right. I'll just play. And then we try and take 3 others from that T2 kind of edematous region, which is thought of as the infiltrative tumor cells, where the infiltrative tumor cells lie. We use the MRI to localize these locations during surgery. So as for the tissue analysis, we then take these biopsies and we analyze something called the copy number aberration, which typically a diploid cell will have 2 copies of a gene. So they'll have a copy number aberration of 2. Numbers that are larger than that are considered amplified or a gain in that gene. And often that means that specific cell is upregulated in that gene and promoting whatever that gene does. So for example, EGFR will be promoting more receptors on the cell surface, which can interact with growth factors and encourage the tumor to grow faster or migrate faster. So we're quantifying that in each individual biopsy. And here on the right-hand side, you can see a figure that summarizes what we have for 95 biopsy samples across 25 patients. We see a spread. We see some biopsies that have neither EGFR or PDGFR amplified, some that are only EGFR amplified, a few that only have PDGFR, and some that have both. So we let a copy number aberration of above 2.2 be considered amplified in this example you'll see here. There's some debate about what that threshold should be, depending on the mix of normal tissue and tumor tissue in the samples. We've chosen a pretty low threshold to make sure that we're really detecting anything that is amplified in our biopsies. Just to give another summary of this data, here's the average that we tend to see in a spider plot of the EGFR only, neither, PDGFR only, and both. And so the mechanistic model that we use, we are interested in modeling the 3 different populations of interest: the EGFR amplified subpopulation, the PDGFR amplified subpopulation, and another population of tumor cells that is not amplified in either of those genes. To make the model make sense, we used a diffusion term based on a Painter and Hillen approach to volume filling. This paper that came out in 2002 by them, for those interested. And we use reaction terms that have some interaction between the EGFR and PDGFR. So this term alpha here is really our key parameter in the model. If alpha is positive, then these 2 subpopulations will be promoting each other. If it's negative, then they'll be competing against each other. And if it's 0, then they'll neutrally interact for space. We still have a space term here, but they won't be actively against each other or with each other. So what does this look like? This is similar to some of the slides that John Nardini presented earlier, especially that purple line. And when alpha is 0, the sum of these equations actually becomes the Fisher KPP model. So we have the sum of everything shown here in purple. Red is the PDGFR only example here. Blue is the EGFR only, and N would be the yellow, sorry, would be the neither. We have to choose a threshold of detection in the model. That's the level of cells that we can say that we could accurately see in a biopsy. And we've chosen that to be 10% of the carrying capacity of the model. The reason for that is that traditionally in patient-specific Fisher KPP models, we choose a 16% threshold in our maximum cell density to represent what we see on T2. Some of our biopsies, though, are outside of that region. So we've chosen a slightly lower threshold to represent that. We can simulate various interactions, various values of that alpha term. We can simulate various migration and proliferation rates, which is a lot, again, what John Nardini spoke to of the fast, the slow, the diffuse, and the nodular examples. And we can allow for the EGFR mutations and PDGFR mutations to occur at different tumor sizes and various locations. What we did in the model is we chose those locations, or we didn't choose them. We allowed the logistic growth to act as weights for where those mutations might occur. And traditionally, mutations occur during proliferation. So the regions that are proliferating more are more likely to be the location where those mutations occur. So some results from this. We see here on this example here, the solid lines represent those averages I presented earlier for the data. These are subject to change with the introduction of more biopsies. We could be more sophisticated later on with the variance we see in the data too. But here's just an example. So what we're trying to do here is match the solid lines with the data, with the simulations. Each point on this figure represents 100 different simulations. It's the average of those for different migration and proliferation rates. And as you go across the x-axis here, you see we're changing the alpha term. And you can see that with different alphas, we end up with different proportions of these simulations with different upregulated amplified subpopulations. So for example, and here, we introduced EGFR pretty early, so when the tumor is very small, and PDGFR early at the same time point. If we have competition on the left-hand side here, then we don't really see many regions where both of these subpopulations occur. And that makes sense because if they're competing with each other, they're actively suppressing each other. So if both are present, they're kind of competing and they don't really pop up together. Whereas if we have a strong cooperation between these subpopulations, on the right-hand side, we see a lot of regions where they're both amplified because they'll both promote each other's growth. And then you can see, you know, as we change alpha, we have a transition between those two extremes. But that's not the whole story. We can also introduce these mutations later on, both at the same time, or in this example here, we just introduce PDGFR later as you go towards the right of the screen. And you can see how that changes the dynamics as well. So for example, if we introduce PDGFR a little later, we see more regions where there's only EGFR. And that's because it's introduced earlier on in the tumor growth. It has more time to establish before the PDGFR comes to either compete or cooperate with it. So we see a lot more of this red line here. And in this example in the middle, we've pointed out two parameter sets for alpha that match the data the best. And you can see that they're clustering around where alpha is approaching 0, meaning that these subpopulations aren't interacting in terms of our best fit to the model. However, if we then introduce PDGFR later still, we see that our best fits now point towards alpha being positive, suggesting that these subpopulations are cooperating. So obviously this is an area that needs further research. If we are introducing, like we don't know when these subpopulations will be introduced per patient, and that obviously affects our outcome of this alpha term, which we're very interested in. Even still, if we then introduce the EGFR later and the PDGFR later, but we give them an advantage, which is pretty realistic because these subpopulations need some kind of evolutionary advantage to, you know, spread throughout the tumor themselves. So for example, here we gave EGFR a 20% proliferation advantage against that neutral population and a 50% motility advantage against that neutral population. And PDGFR, we only gave a 20% proliferation advantage. We see now that our best alpha is pointing towards competition. So now we have an example of all three. So yeah, it can get messy pretty quickly with the way that we've set up the model so far. But we need more sophisticated techniques to really tease out that relationship. One thing that we've done more recently is an ABC rejection on a lot of simulations. Again, each point here represents 100 different simulations. We've chosen our priors just to be uniform for this case. We have an EGFR prior. That's when the EGFR is introduced in terms of the tumor size. Same for the PDGFR. Alpha runs again from -5 to 5, representing those strong competition and strong cooperation examples and everything in between. And then D and rho, which represent migration and proliferation here. We choose the same values that John Nardini showed to represent kind of the average we see in data for the Fisher KTP equation fits. If we look at this figure on the right here, we see that our best fit was for an example where EGFR was introduced earlier than PDGFR, which again makes sense with the data because we do see a lot more regions where EGFR only exists in our biopsies. And our best alpha suggested, again, a slight shift towards competition. If we look at this from a different angle, ignoring the z-axis, just smushing everything down, we see that a lot of our accepted simulations that were below the threshold in our ABC rejection cluster in regions where PDGFR is introduced later. So we think this is a little promising that EGFR might be an earlier mutation in our data. We then ran another example of ABC rejection, focusing a little bit tighter on our parameters. And we again see an example of our best fit being where EGFR is earlier than PDGFR. Alpha is a little stronger now in terms of competition. And also we noticed here in this example that we do see a clustering towards alpha being negative. So maybe we are pushing to a competition example. You can find out more about this work. We had a published abstract for the Society for Neuro-Oncology conference last year. And we have a preprint that just came out with submission, hopefully that'll be published pretty soon. If you can use your phone, hopefully to scan these QR codes, it will take you to these URLs. Oh, excuse me. So I've spoken so far about these 4 different aspects of this work that all lead together towards model selection. Model selection being, what is that alpha term? But I haven't spoken about machine learning, and that is a large aspect of this project, which is currently a little disjointed. But we want to connect these two together to try and really tease out what's going on the whole of the MRI. So can we associate the genetic makeup of those biopsies to what we see locally on those image localized, on those MRIs, remembering that we have those biopsy locations localized on the image, and then use that relationship that we've ascertained through machine learning to fill in the gaps on the MRI and create what we believe with certain accuracy, or with some probability, where these subpopulations are. Furthermore, we're interested, does EGFR occur more towards the infiltrative tumor or towards the center of the tumor? Questions like that. But furthermore, we want to then use this machine learning output in our mechanistic model, sort of as more data to give us a better sense of what's going on. We also could update the model to include 2D space, maybe on a realistic brain, so we could compare side by side these mechanistic model outputs with this machine learning outputs. So that's pretty much just speaking to what I spoke to you so far. In this example here, I just chose at random from some preliminary results. We do see all 4 regions occurring. Well, we have EGFR only, PDGFR only, neither of the subpopulations being present, but tumor is still there, or both. So this kind of speaks to the fact that we do at least see these 4 different things happening also in machine learning, like we do in the data. So preliminary results from a machine learning model, we tried Gaussian regression. We did a leave one patient out analysis, which takes into account all of the patient's biopsies bar this one patient, but does include that patient's image in training. And then we apply the trained model to see if our biopsies, see if we predict the correct amplifications or not for those specific biopsy regions on the MRI. We determine features on an 8x8 grid, which slides along the image. We chose quite a large grid to represent uncertainty, or a little uncertainty on where those biopsies are taken from. Because although we do register the brain to the machine that we use to localize these biopsies, there is some uncertainty in that. With the brain shift that occurs during surgery, the head might be slightly in a different position than we had registered to. We also use transductive learning on our feature selection, which reduced our uncertainty of our prediction. So we had regions where of significance, where we had we were pretty sure that was true. And we did have reasonably good accuracy, sensitivity, and specificity for this. However, this is an ongoing clinical trial, and with the inclusion of more data, especially our recurrent samples, which is the second or maybe even later surgery for the patient, where they then extracted more biopsies, we didn't see as good accuracy in our methods, using our methods. So we're kind of still currently working on those, which is why we're focused in this talk as well on how we could apply the mechanistic modeling straight to the data. But ideally, we do want to include the machine learning in that process too. If you want to find out more about those methods, I'm by no means a machine learning expert, but there is a preprint that just came out on medRxiv. Again, you could scan a QR code and hopefully it will work and take you to where I hope you're going. And this is a paper that's in submission too. So in summary, I've introduced a PDE model of GBM growth that considers these genetically distinct subpopulations, which is a step further than we traditionally do with the Fisher-KPP equation. We want to use these machine learning maps to predict these upregulated genes to then inform further the machine learning model. There's a lot more to do. Our future directions, for example, we want to run a sensitivity analysis on the PDE model to really see how alpha interplays with those other parameters, which can definitely change our best fit. We want to connect machine learning, like I mentioned. Currently, we only have one time point per patient, so we're waiting for the patients to progress so we can collect more samples, more time points, and just see if we can apply this in our current setting, or does it work? Basically, can we validate this? We also need to think about how we can consider the spatial aspect of our data. We intentionally collect a broad range of biopsy locations from the enhancing region on T1 GAD and the T2 edematous region. Can we include that in our model? In which case, we'd have to make our model a little more sophisticated, which may introduce more parameters and may make everything more complicated in that sense, but could be worthwhile. So with that, I'll wrap up my talk by thanking a bunch of people who are involved in this. That photo on the right there is my lab before we couldn't be near each other anymore. The primary people involved in this work, Beth Ann Morris, she's a PhD student at Nottingham. She's done a lot of the modeling under Marcus Owen, her supervisor, and my ex-PhD supervisor. Kristen Swanson, who's my current supervisor here at the lab. Leland Hu is a neuroradiologist here. Nyan Tran, he analyzes a lot of the genetic stuff. Jing and Luja, they're involved heavily with the machine learning side of this. We're funded by the MCI under a UO1, and there's another QR code there if anyone wants to go check out our lab website. And thank you everyone for listening, and I'll take questions if there are any.